Cable-stayed coverings for large-span public buildings. Authors: Radomir, Timchenko, Stanislav, Popov, Dmitry, Krishko, Goodary, Rajeshwar, and Aleksej, Aniskin. The interest in cable-stayed coverings, which is manifested by many researchers, designers, and builders, is common and becoming a natural engineering problem to resolve. This is helped not only by the economic advantages of buildings used, but also by the development of calculation methods and design techniques. Plausible results associated with the study of static, dynamic, and kinematic properties of cable-stayed systems with the use of computer technology have been achieved. Positive attempts have been made to solve problems of optimal design. Currently, scientists are considering issues related to a choice of constructive schemes of a cable-stayed covering, study of the stress-strain state of cable-stayed systems, methods of solving equations, optimal design of cable-stayed systems, dynamics of cable-stayed systems, design of cable coverings. The relevance of the study is determined by the use of a constructive scheme of coverage, which allows the use of a lightweight roof structure using modern composite materials. The outstanding works of local and foreign scientists in this field over the past 30 to 40 years are to be commended and encouraging for future research. As a result, buildings and structures using cable-stayed systems are quite widespread. Coverage of public and industrial long-span buildings, cable-stayed bridges, and overpasses. But there are also problems that hinder the spread of cable-stayed systems in construction. This is, first of all, the lack of regulatory framework for the design and calculation of cable-stayed systems. All parameters and recommendations for design and research can be found only in the works of scientists who are specialized in this field. Hanging cable-stayed structures are mainly used to cover large-span buildings, structures of various types, such as stadiums, gymnasiums, entertainment and trade buildings, where they are most cost-effective and aesthetically pleasing. Buildings and structures with cable-stayed hanging coating, in contrast to the dome and cylindrical coatings, allow to cover the area of buildings, structures of much larger size without economic losses, while easy to manufacture, install, and operate. However, with increasing the area of the cable-stayed cover, respectively, increases the support forces in the cable's flexible threads, which are transmitted to the external support, in which case it is necessary to increase the stiffness parameters of the external support circuit. Local and foreign experience of building structures using suspension systems are described in the works of Kirsanov and Dmitry, Krishko, Timchenko, Goodary. The purpose of the study is to analyze the cable-stayed coverings used in long-span public buildings, finding their optimal parameters and choosing an efficient and economical type of roof. To achieve this, it is necessary to solve the following problems: to investigate the state of issues related to the design and calculation of cable systems, to find the expedient constructive scheme of a cable-stayed covering, to substantiate its choice, to study the construction of the roof of cable-stayed coverings, to develop a new type, and to adapt it to the chosen structural scheme. The following are examples of cable hanging coatings. Features of cable hanging covering: 1. Belt systems of hanging coverings. 1. To cables with a diameter of 40 millimeters with a step of 1.5 meters. 3. Reinforced concrete support beams. 4. Reinforced concrete panels. 5. Anchor foundation. To belt systems of hanging coverings: A. With compressed racks, struts. B. With stretched racks, pendants. C. With a central hinge. D. With struts and pendants and with 2 hinges in flight. A. With a triangular lattice. 1. To cables with a diameter of 40 millimeters with a step of 1.5 meters. 3. Reinforced concrete support beams. 4. Reinforced concrete panels. 5. Anchor foundation. Cross systems of hanging coverings: cable grids. 1. Bearing cables. 2. Stabilizing cables. Combined cable hanging coverings: A. Single console. B. To console. C. D. Cable combined system with radial and parallel arrangement of cables. E. Cable system with a girt upper belt and a triangular lattice. F. Hanging system with the transfer of the strut to the stiffening beam. Rope cover networks saddle mesh with support contour. The following are examples of cable hanging coatings indoor arena, livestock pavilion, in Raleigh, USA multi-diagonal sports facility, Scandinavium, Gothenburg, Sweden spectacular and sports facility, Madison Square Garden, in New York, USA. David L. Lawrence Convention Center in Pittsburgh, USA. University of Chicago Athletic Center, USA. Volkswagen Complex, Wolfsburg, Germany. Cable tower cooling tower with central pylon, Germany. Diagonal cable installation diagram cable cooling tower. Stadium in Calgary, Canada. Wembley Stadium, London, UK. Spiros Lewis Stadium, Athens, Greece. The problem of designing a cable-stayed cover is considered on the example of a circus building. It is designed on the basis of a typical circus project. The cable-stayed covering covers the auditorium of the circus with a diameter of 48 meters. The design of the cable-stayed cover took place in several stages. First stage, choice constructive scheme. Second stage, choice of roof design. Third stage, calculation and selection of preliminary sections of cables. Roof constructions in the form of a cable grid with an orthogonal cable network, I option, and a network of cables formed by two groups of stabilizing cables, I option, were considered. Choice of constructive scheme. 1 option, cable-stayed cover of the circus auditorium with an orthogonal cable-stayed grid, according to a typical project. 2 option, cable-stayed cover of the circus auditorium with a cable-stayed grid formed by two groups of stabilizing cables. The maximum weight of lightweight types of roofs is normally limited to 40 to 60 kilograms /m2. The roof structure in the warehouse is used for implementation: 1 waterproofing layer, 2 metal membrane, 3 vapor barrier, 4 insulation to connect the cables to each other. A metal plate is used, to which the cables are fastened with a bolted connection. Fastening of cables in knot is compulsory. To fill the triangular cell, a triangular plate of insulation is used. It is reinforced externally with a composite material. Reinforcement is performed as follows. 2 triangular plates of polyfoam are placed on top of each other and fiberglass membrane is laid between them, which is fixed at the edges of metal plates with a thickness of 3 millimeters, which are fastened together with a bolted connection. This structure is externally reinforced with rolled fiberglass. Fastening of plates among themselves occurs by means of metal welded details of channel section. There are metal hooks which fastens the plate to the cables. The scheme of laying of plates of a heater is also presented. In design practice, the magnitude of the breast dressing system, the magnitude of the forces of interaction of the cables, is often set, provided that the stabilizing cables are almost excluded from operation at full load on the coating. In this case, the share of interaction forces in the total load on the carrier thread is small, and the determination of the forces in the grid, carried out by this method of calculation, is accurate enough to assign cross-sections of threads in advance. The curves of the conditional volume of the cables for different values of the relative sagging arrows of the stabilizing and supporting cables, at different values of the coefficient QK. The graphs show that the most economical are the options with QK equals 1.3 and with larger values of the sagging arrows of the supporting cables. It is possible to investigate the dependence of the degree of operation of the stabilizing cables on the load on the coating. The graphs show that the most effective stabilizing cable works at a load of 0.5 to 1.2 pot, at a load of 2.6 to 3.0 pot becomes ineffective, and at lower values also begins to perform the functions of the supporting cable, from which it can be concluded that the most rational type of roof for saddle-shaped cable-stayed structures is a light roof. Tables load on the coating. 1 option to option. Relative costs of concrete and steel tables, the result of the optimization problem. 1 option to option. Conclusions. 1. Cable-stayed structures are more economical compared to other types of roofs, but their widespread use today is complicated by the lack of design and calculation standards, as well as design solutions dated 30 to 40 years ago. 2. The constructive scheme of a cable-stayed covering formed by two groups of stabilizing cables is presented, and it is shown that an elementary triangular cell is formed, which allows the use of fragile roofing materials. 3. A new type of building plate is proposed, consisting of triangular plates of fiberglass reinforced insulation. This makes it possible to facilitate the design of the building without reducing the strength characteristics. 4. An optimization problem was solved to design the cable-stayed cover and determine its characteristics. As a result, the optimal cross-sections of the cables were obtained. For comparison, the optimization problem for a typical building variant was also solved. 5. The calculation shows the inexpediency of using a heavy roof structure for saddle-shaped cable-stayed coverings due to the exclusion from the work of stabilizing cables with a large weight of the roof. 6. The developed design of a cable covering is more economical in comparison with the typical design of a roof, with reduced materials and more effective performance of the elements. Thank you for the attention.